So in last class we discussed about the dark effect, which is weak field dark effect. We concluded that weak field dark effect never observed because the fine structure components of the H alpha line has not been completely resolved. So the weak field dark pattern never observed. Okay, so that was the last class. We discussed about the weak field dark effect. And in today's class, we will discuss about strong field dark. Strong field dark. A strong field for the case of hydrogen atoms, you consider, is one for which the interaction energy between those electrons and the field. So basically in this Stark effect, we are applying electric field, as in the case of Zeeman effect, we are applying magnetic field. So we are applying electric field here, applying electric field. Electric field, let us denote that field as F. This is electric field F. Okay. Or you can put EF also, no problem. So, or any symbol you can use. So we are applying electric field, and this electric field is now it is strong. It's strong electric. Okay. So in the last class, we discussed about the action of those electron on the spectral line. Sorry, action of those electric field on the spectral line if the electric field is weak, and we call such actions or such phenomena as weak field Stark effect. In this case, we are applying strong electric field. So we have atom here, that sample here, and we are applying electric field like this. Electric field I will present it as F. Electric field which is in the Z direction. This is the Z direction. So we are applying this electric field in the Z direction, and this electric field is very strong. Okay. So strong means that, what is this strong? Strong means that which have the interaction energy between those electrons and the field is greater than that of the magnetic interaction energy between electron orbital momentum and the spin moment. So in this case, the interaction energy between electron and that electric field F is larger than the magnetic interaction between those electron orbital momentum or orbital angular momentum and spin momentum or spin angular momentum. So that is what we call it as the strong here. Strong means the interaction between the electron and the electric field F is larger than the interaction between the magnetic interaction between the electrons orbital angular momentum and spin angular momentum. In other words, we can say this stark splitting is higher or larger than the fine structure split. So what is this fine structure? Fine structure splitting is coming because of the magnetic interaction between those L and S, orbital angular momentum and spin angular momentum. But the stark splitting is coming from the electric field interacting with those electrons. So the stark splitting will be higher or larger than those fine structure splitting, or the interaction between interaction of that electron with the electric field is larger than the magnetic interaction of electron orbital momentum and spin moment, electron spin moment. So this condition we call it as strong field stark. Okay, this is what is meant by strong field. Okay, when the stark splitting is larger than the fine structure, or the electric field electron interaction, which is larger than the magnetic interaction between the electron orbital angular momentum and spin angular. Okay, so this effect of homogeneous electric field that we are applying to the sample, like here, this electric field that we are applying in the z direction, and the sample is placed inside this electric field. And suppose this is the homogeneous field. There is no variation in strength of this field at any position. So these are homogeneous fields. So the effect of this homogeneous field parallel to this z-axis, we are applying to the parallel to the z-axis on an electron, which is moving in that Kepler orbit, is different from that of a magnetic field. So for example, if you consider the electron which is moving like this, a closed loop, we have nucleus here, electrons are moving like this. So this is a closed loop or closed orbit. So this is the Kepler elliptical motion. So if you consider this case, this is the ordinary case. Normally electrons will be revolving around the nucleus in an elliptical path like this. But when you are having that electric field, when you apply the electric field in the z direction, then this is not the scenario. This is not the scenario because the center position from the nucleus, it will be shifted because of the action of this electric field that will have some force on this particular electron, and that will change its orbit. Okay? If you consider, let's say this case, let's consider this figure. Here, so we have the electron which is revolving around the nucleus. So this is your nucleus here. So this is your nucleus. And you are applying the field in this direction. Here, this is your F, and this is in the Z direction. And the electron which is revolving around this nucleus, so it will be having different path with the effect of this electric field, external electric field. So if you consider that here, let's take another view of that electron orbit. So let's say this is your orbit. So the electron will be going like this, will be starting from here and going, let's say this is going like this. Then when it come here, because of that electric field, it will choose another path. It will not become a closed path. Instead of that, it will choose another path and it will go like this. It will take another path again. Because of that external electric field. So that electric field will cause the nucleus or the average center of mass of that the orbit, which will not be coincide with the nucleus. Okay? So the center of mass of that electron, which is revolving around those nucleus, will be different with the presence of that electric field. You can see it from here. So if you consider this electron which is revolving around this nucleus, so initially its path was like this. Okay. Then it is moving in some another way. Your electron which is moving in a different orbit, in a different way. So it is not going to form a closed orbit. Instead of that closed orbit, it will form an open orbit, but it will be confined in this region. You can see in this figure, this rectangle you can see, this particular rectangle you can see. So in this rectangle, it will be confined. So it can choose any orbital path which can touch this particular rectangle. So it can go like this. In the first case, it can go like this. The next time it will touch somewhere here and come back here and touch here, and it will go again in some different path and touch some other position and come back. So it will be having different path instead of that closed orbit with the presence of electric field. So when you are applying this strong electric field, means that the electric field in such a way that the Stark splitting is larger than fine structure splitting, then the electron center of mass of those electrons which is revolving around the nucleus will not coincide at the nucleus position. Okay, the center of mass will be different at in each time, and it will not be at the nuclear position, or it will not be at the nucleus. Okay? So center of mass will be different. So for example, if you consider in the first case, you consider we are having this kind of orbit. In the first case, it is not closed. So in this case, you have center of mass here. Let's say the nucleus is also in the same position here. So center of mass will be at the position of the nucleus. Both will be at the same position. Center of mass of this electron, which is revolving around the nucleus, will be at the same position of that nucleus, because nucleus is at the center. But next time, this will choose some different path. It will take some different path like this, and this center of mass will be shifted from that initial position. So it will be having center of mass somewhere here. Then next time it can choose some other path, and the center of mass will be in a different position. So slightly that center of mass will be is going to be different because of that external electric field. The electron move in a non-closed or an orbit which is not closed, and it will take some different path because of that external electric field, and that paths are confined in these two regions. So in each time it will touch in these two region, but within that region it can go in any direction. Okay. So this effect of electric field or homogeneous electric field on the on an electron moving in circular ellipse, which will be different from that of a magnetic field. That from that of magnetic field. So if you are having magnetic field which is applied to these atoms, and it do not change its that elliptical path, it will be still in that circular path, closed circular path or closed elliptical path, but it will not change its path into a non-closed orbit. But when you are applying electric field, your path orbit will become a non-closed orbit, or we can say that with the application of electric field, the electron will move in an orbit which is not closed. Okay? But if you are having that magnetic field, if you are applying magnetic field, then you will be having that change in its angular momentum direction. It will be there, but it will not be having any kind of unclosed orbit. It will be having always it will be having that closed orbit when you are applying magnetic. Okay. So each time when you are applying electric field, its path will be changing, and it will confine. It is going to confine in this region. From here, it will be confined in this region. So it can touch here in this position point. It can touch this point. It can touch this point. It can touch this point. Any point it can touch in this rectangular region. So that its center of mass will be different in each case. So it will not coincide with that of nucleus. Okay. But when you are applying magnetic field, this will not happen. That precision will be there. That orbital, for example, if you are applying, for example, if your angular electron which is moving like this, and your angular momentum is in this direction, and you are applying magnetic field in this direction, then that precision will be there. This precision will be there. Okay. But electron will be moving in that closed orbit when you are applying that magnetic field. But when you are applying this strong electric field, the electron will experience that force, and its trajectory will become different in each case, and it will not form a closed path or closed orbit. Instead of that, each time it will be having different orbits, and hence its center of mass will be different. But still, it will be confined in this range. Okay? So in this range also, it can touch any of this. If you got like this, so it can touch any point in this particular region. So next time when it comes, it can come like this and touch this point and go in some different path like this and touch this point and come back. So each time its path will be different. So the center of mass of that electron will be changing in each case. So it will not be coinciding with that of the nucleus. Okay. So for this particular case, the center of gravity or the center of mass, center of gravity. So the center of gravity means that center of that particular electron orbit in each case, if you consider, it will be different for each case. Okay, that is the center of gravity, center of that orbital motion of that electron. That will be different. So center of gravity is going to be of electron averaged over its orbit does not coincide with the nucleus, and thus forms
അഫ്നാനെ ജോയിൻ ചെയ്യിപ്പിക്കാൻ പറഞ്ഞാണ്.
ഞാൻ ഏറ്റായിട്ടല്ലോ ഒന്ന്.
അവള് കൊറേ നേരായി കേറാൻ നോക്കണ്ടായിരുന്നു.
ഞാൻ കേട്ടണില്ല.
അവള് കൊറേ നേരായി കേറാൻ നോക്കണ്ട്, പറ്റണില്ലായിരുന്നു.
അവള് 3:30 എത്തി. Nucleus and thus forms an electron dipole its orbit does not coincide with the nucleus and thus form an this will form an electric dipole. This will form an electric dipole. Okay. And the torque on orbital dipole by the electric field causes precision. Of orbital momentum about z axis. So since the center of gravity of this electron, which will not coincide with the nucleus, okay, so hence there will be an electric dipole. It will form an electric dipole in that atom. And if you apply some electric field to this particular electric dipole, or you can take any dipole, electric dipole with some negative charge, negative q and plus q and minus q, which is placed inside an electric field, then that particular dipole will experience particular torque. Okay, so this is minus q, this is plus q. So this is just a representation of the dipole. Let's take in this particular case, we can take this as electron, and this is your nucleus. Okay. So in this case, if you apply any electric field, let's say I'm applying some electric field in this this direction, electric field in this direction. So we have a force of E times let's say this is my capital E, electric field E, and that will be EE, and this will be minus because electron are having minus charge. And here we have n times e. Let's take n is the charge of nucleus, then it will be minus, sorry, this is plus n times e will be the force experienced by this charge in this electric field. So that force will be nothing but q into v, charge in the electric field. So that will be the charge of nucleus is n times the electric field is e. And in the case of electron, we have minus e times capital E. So when there is a force, because of this electric field, there will be a force on this electron, and this electron tries to rotate like this. And at the same time, when you have this electric field in this direction, there will be a sorry, this one will be rotating in the opposite way because it is minus. You can check that direction. Let's say this is your electric field. So I think it should be in the opposite way, right? We just check this direction. Anyway, it will be having some torque effect here. So if you are having an electric dipole which is placed in an electric field, then there will be a torque which is acting on this particular electric dipole because of that force experienced on each of those charges, minus q and plus. So similar effect we can have here also, because initially the atom which is in the neutral state, okay, atom which is in the neutral state, because the center of gravity of those electron, which is coincide with that of nucleus. Okay, so when that is going to be having some change, then there will be some separation between those negative and positive charges, that nucleus and electron, and that will create an electric dipole inside that atom because of that external electric field. And further application of that electric field will cause this torque effect that will form the precision of orbital angular momentum about the z-axis. So initially, we are having that nucleus and electron which are coincide. So just draw it at like this. So electron and nucleus which are coincide like this. So the center of gravity will be of that electron. Let's say this red color which is in the electron, and this one that blue color which is in the nucleus. So these two will be having same center of gravity, or the position, or the center of gravity of this electron which is revolving around the nucleus will be at the center of that nucleus. So they are coincide each other. Okay, so if you are applying some electric field, the electron will be having some experience of force, and the trajectory of that orbit will be different, and it will create some change in this particular center of gravity of this electron, and these two will separate a little bit. Okay, so a very small separation will be there between this electron and nucleus. That will create some dipole moment because the charge, two opposite charges are separated now. Minus charge and plus charge are separated. So that will create the dipole, uh, and uh, and that dipole is in that electric field, so that the that experience torque, which will result in the precision of that orbital angular momentum about that z-axis in the field direction. So that is the basic principle of the strong field charge effect or strong charge effect. Now, if you further consider that orbital angular momentum, so in this case we can say the orbital angular momentum L is not a constant now. because the path is going to be different at each time, and the center of gravity will be different. So the L vector, which will not be the same. So the orbital angular momentum L is not a constant, hence it is not a good quantum number to measure any physical quantities. So but the projection of those L, that orbital angular momentum on electric field axis or z axis, that is Lz, which will be given by MLH cross, and this ML value will be that constant for each of those orbital motions. So the orbital angular momentum L is not a constant now, because the path is different for each case. Orbit is going to be having different path, which is not a closed orbit. So L in each case will be different. So L is not a constant, and is not a good quantum number. Good quantum. But if you consider the Lz, which is the projection of L, projection of L on z axis, that is Lz, gives MLH cross, or this projection is given by LH cross. Lz is given by MLH cross. This is the projection of that L. Okay. And in this particular case, this ML is treated as, ML is the electric quantum number. Now, if you consider that energy of those orbital motion of those electrons, which is not having that closed path, that energy will be given by, so the calculation carried out in parabolic coordinate which gives energy as E equal to E0 minus, so I'm going to derive this equation, A0 E by 2Z times F into N times N1 minus N2 minus N. So for E0 is the initial energy, or the you can say that field free energy of atom. So we are talking about electron, sorry, hydrogen atom here. So only one electron, we are having only one electron. So it is E0 is nothing but field free energy of the atom, which means that we are not when the energy of that atom when we are not having any external electric field. That is E0. A0 is the Bohr radius. Bohr radius. Then we have N, which is that principal quantum number. Or energy quantum number, you can say. Then we have, or we can also call this as energy quantum number or total quantum number. Total quantum number. And then we have N1 and N2. This you might not be knowing. So these are some new set of new quantum numbers. Two new. This is parabolic quantum numbers. Quantum numbers. Two new quantum numbers. And this is subject to the condition that ML will be equal to N minus N2 minus N1 minus 1. So ML value should be like this. From that, you can find out what is N2 and N1. And the allowed values for each of these quantum numbers, which are N, can already know this N can take value from 1 to 3, 4, etc. up to infinity. And ML will be having values, as you know, for L equal to 0, it will be 0, L equal to 1, 0 plus or minus 1, plus or minus 2, plus or minus 3, for all those L values. So this can go up to plus or minus L, that is plus or minus N minus 1. Then we have N1 values. So N1 can take values as 0, 1, 2, 3, etc. up to N minus 1. Is up to N minus 1. Similarly, N2 also having value 1, 2, 3, 4, etc. up to N minus 1. So what we just discussed here is that we have first calculated what is the energy of those electron or the atom with the presence of that electric field, external electric field. So that expression is given by this equation, E equal to A0 minus 3 A0 A by 2Z F times N times N2 minus N1. So you don't have to study the derivation part. So this is the energy associated with those atoms with the presence of strong electric field. Okay. And these are the different parameters or unknowns that equations. And then we have this condition for those parameters, for those quantum numbers, or the values of those quantum numbers. Okay. So what exactly this N1? The N1 will limit the electron's motion to the region between two paraboloids, or the revolution, which is beta max and beta minimum. Here, you can see here we have this one. You can take this as eta, or you can take it as beta naught. So this here it is eta. So we have eta max here. Eta max. This is eta min. Okay. So in between these two paraboloids, this one, this is the first one, and we have second paraboloid here. So in these two, I am talking about this paraboloid. This one, this color. This one, that is for eta minimum, and this one is for eta maximum. There are two parabola. This is for eta max. Okay, so the n1 quantum number will limit the electron motion to the region between this eta minimum and eta maximum. This eta minimum, this is eta minimum, and this is eta maximum. So the region between these two is this one. So this is the region between that eta minimum and eta maximum. So that quantum number n1 will limit the electron motion in this particular paraboloid. So actually this is in 3 dimension. So you have to picturize it like that because electrons are revolving around the nucleus in a 3D fashion. Okay, this is not in a 2D fashion. So this will n1 will limit the electron motion in this particular in this two paraboloids, and n2 in the same way n2 you can see for the case of n2. I'll just erase this thing. So n2 also you can see another two set of parabolas. So this one, another parabola, and another one here. So these two are other set of parabola. So that will give you this particular range of values of range where the electron can be confined. So the n2 value will, or n2 quantum number limits the electron motion within this eta minimum. This is eta minimum, and this one is eta maximum. Eta max. So in between these two values, in between these two paraboloids, the electron's motion will be limited. So the n2 quantum number will limit the motion of electron in between this eta minimum and eta maximum. So total this area where your electron can have the different paths, that will be restricted or controlled by these two quantum numbers n1 and n2. Okay, this side, which is nothing but n1, this side is n1, and this side is n2. So these values will restrict the electron path or electron motion to that particular region, this particular region. So the value of n1 and n2 will determine the area by which the electron can have different paths. Okay, so these are the two new quantum numbers. In the same way, you can also define those quantum numbers here. Here you have n2, here you have n1. So this side also you have n1. Here also it is having n1. So this region is also confined to those electron motion, or the electron motion is restricted to this region by using these two quantum numbers n1 and n2. Okay, so that is the importance of these two new quantum numbers n1 and n2. I will just write it here so you can elaborate it in your own way. So n1, which limits electron motion to the region between two paraboloids of revolution in this particular case was that is eta, right? Eta, and in this case it will be eta. So revolution which is having eta. No, this is not eta. What is this symbol? This is. I think this is epsilon or something. Okay, yeah, this is epsilon and eta. I think. So I'm confused with this. So I'll just put it as epsilon. Just check that. Epsilon max and epsilon minimum, or you can take any uh, symbol, beta, alpha, or anything in that figure. So that will be confined between this epsilon minimum and epsilon maximum. So that first paraboloids will form the region between this epsilon max and epsilon minimum, and the quantum number corresponding to those two paraboloids is n1. So that n1 will be limiting electron motion within that area. In the same way, n2 you can say in the same way n2 limits the same electron motion with the region between two paraboloids of, or you can just put it another two paraboloids of having a revolution um, eta max and eta minimum. Right? You can write it in your own way. Eta max and eta minimum. So n2 limits electron on the other half, other area, the part of that paraboloid. So the electron has three periodic motions here, different motions. One around the field F given by ML, and one each along the beta and the eta coordinates, and that connects the that coordinates of that eta and beta. Sorry, in this case it is eta and epsilon. Okay. So I have again here the symbol in that figure. I am having mu. I think. Right? So this is okay. It is eta only. So this is eta max and eta min. That's right. So the coordinate or the coordinate of this eta will be given by n1, and that of sorry, this is epsilon. Coordinate of this epsilon is given by n1. This eta is given by n2. So basically, there are 3 degree or 3 different motion for this particular electron. So the electron can have a motion which is just explained here. I'm just erasing these things. The electron can have motion, 3 different motions. One, the electron is revolving like this. Okay, it is not a closed path. So it is moving around this field. That is first case. So it can rotate around this field. That is first periodic motion. Second one is that it can have it can be in this range. It will be touching in this range. in this particular area. Okay. So that electron can have the free periodic motion which will be along this, in this case it is epsilon, along this epsilon as well as along this eta. Okay. So with respect to this eta value, this two eta minimum and eta maximum, I can specify that electron motion in each cases. Similarly, with respect to this epsilon minimum and epsilon maximum, I can also specify the electron motion. Okay. So there are three different motions or periodic motions available for the electron. So one is this rotational motion about this field or the z direction. Second one is about this eta, and third one is about this epsilon, which means that we have three different coordinates to represent this particular electron motion. Okay, and the coordinate corresponding to eta will be given by this n2 quantum number, and coordinate corresponding to this epsilon will be given by this n1 quantum. Okay, so basically there are three. So the electron has three periodic motion. So in that one around field F, and which will be given by quantum number ML, and one each along beta, and in this case it will be slow, right? Have written it as beta, so it's getting confused. So it will be with that of, I'll just put it as beta. One is coming, so we'll just put epsilon first, and second one is eta, right? Epsilon and eta. You can change this symbol with the beta or alpha or anything. I'm just putting as epsilon and eta. Okay. So these two, one around F field F, which is given by ML quantum number, and one each along this epsilon and eta, given by for epsilon it is n1, right? And so n1 and n2 respectively. So n1 corresponding to epsilon, and n2 corresponds to that the eta. Why this one is given by ml? This is from that precision. We already know that quantization. We already studied this. So if you are having your L value, L can take different values depending on that theta angle. So the projection of these values, this L, this will be that projection of those L on z axis will be given by that ML. So if you take these two projections, for example, so this will be your ML values. Okay. So if your electron which is revolving like this, or if it is having some different angle, so it will be giving some different path like this. Precision will be different, angle will be different, precision will be different. So we'll be having different ML values. So this is the electron's motion with respect to that field. This is the precision. So electron will be moving. You have to be careful here because the electron will be moving like this. For example, if you consider this particular angular momentum, then the electron will be moving like this. So electron motion will be like this, so that your angular momentum will be perpendicular to that electron motion. Okay. And that angular momentum will be precising about this applied field. So don't get confused with the electron motion with the precision. So the precision will be by the angular momentum, and the electron will be moving in a different orbit. Electron will be moving in this way, and the angular momentum is perpendicular to that electron motion of that orbit, plane of that orbit. This is the plane of that orbit. Perpendicular to that, your angular momentum L will be there, and this L will be precising about this applied field. Okay, so the electron motion around the field, which is nothing but this one, that will be given by ML values. So for each ML, this motion will be different. For example, if your electron is moving like this, then your L is like this, and you will get projection at here. But if your electron which is moving in a slightly, like for example like this, okay, if it is moving like this, then perpendicular to this direction, your angular momentum will be like this. So it will give me some another ML value, different ML value. So these two ML values will be different. So the rotation of those electron about that around that electric field will be given by those quantum number ML, which can be given by quantum number ML. Similarly, the electron motion within that two paraboloids, that region will be confined between this eta max and eta minimum. That will be given by the quantum number n1 and n2. How that is possible? I will just explain that. So if you consider that particular area in between that eta max and eta minimum, I will just explain here. So let's take this is your regime. So remember that this is in 3 dimension, not in 2D. I will just explain it in 2D. So this is your N1 and this is your N2. So suppose that electron which is revolving around the nucleus and coming in this particular way and hitting somewhere here and going back. So it is hitting at this point. Okay. Now let's take the eta minimum N1 which is having minimum value here. So when it comes to this point, it will be having maximum value at this point. Okay. So N1 will be having different values. So if you consider this particular value of N1, that will be having some value. Similarly, if you consider N2 at this 2 point, so it will be having minimum value at this point, maximum value at this point. So where is this electron hitting in this region? This point. This point it is hitting. So you can get this coordinate. So you can get 1 n1 comma n2 value. And if that electron is coming in a different path in the next time and hitting somewhere here and going back like this, for example, it is coming and hitting, going back like this. So your point is here. So you'll be having n2 value here, and your n1 value will be somewhere here. So again, you will get n1 and n2. So you can specify the motion of those electrons with these quantum numbers, with the application of those electrons, electric field. The electron motion can be specified by using the values of ml, n1 and n2. Why? Because we do not have the value of L, because L will be different in this case because of that gravity, center of gravity is different in each case. So we have to take some different quantum numbers, and these are the two new quantum numbers which will help us to define that orbit motion of electron. Okay. So that is the role of N1 and N2. Now we will just go to the energy in terms of wave number, that is delta T, that will be given by 6.4 into 10 to the power minus 5 divided by 3, divided by Z, right? And times F times N times N2 minus N1. Okay. So this is the this is a constant. This is constant. This is same. You can see it from here. Whatever we have written for energy, okay, that is same expression. So here we have energy of the atom with presence of field. So E0 is the energy of atom without field. And if you take the difference between these two, that is the energy of atom with field and without field, that is nothing but E minus E0. Okay, and that will be given by this particular value. And if you consider this is constant, this much of values are constant. If you substitute all those values and put it in there, then you will get this particular expression. And you have to take that in wave number fashion, which means that you have to divide that by Hc. Energy by Hc you have to do. Then you will get this particular constant. After dividing with Hc, you will get this constant. And all other terms are same. Divided by Z into F into N into N minus N. So all those things are same. So don't be afraid of this. So delta T we usually take minus delta T. So since we have minus in here also, so that we'll just take it as delta T. So that is the spectral shift. Or we can say that this is the shift in wave number. Delta T is nothing but the shift in the wave number. The previous one was the energy change. Okay, this is the wave change in wave number. So how we'll get that? So we have written something E equal to E0 minus something. Okay, so E minus E0 will be minus of this something. And if you take this as minus delta T, so delta T will be given by this. So this, this divided by Hc you have to take. So divided by Hc, we have to, here also we have to take divided by Hc. Then this will become minus delta T. Energy divided by Hc is wave number, change in wave number. So this is change in energy, this is change in number. So that will give me minus of something by Hc. And if you put all those constant values and calculate that will give you this particular. So this is in wave number. I will just write this as A times F. So A is where A is all other values, that is Z 6.4 into 10 raised to minus 5 by Z into N into N2 minus N1 is A times the field. How much field you are providing to this particular. Okay, so this will be in centimeter inverse because it is in the wave number we are considering. So in the case of hydrogen, for hydrogen, what will happen? Z will become 1. For hydrogen, Z is 1. Z equal to 1. If you consider Stark effect for the case of hydrogen, so the delta T value will be nothing but 6.4 into 10 to the power minus 5 times F times N into 10 to minus N. So this much of centimeter inverse. Now, as we discussed for the Pascal-Back effect, okay, we have some small correction with the possibility of LS coupling. Okay, so the with the correction of small possibility for LS coupling. So if you consider that correction, we discussed earlier also the same correction, then we have to add that plus AMS and A times ML into MS term. So that with correction delta T will become, this delta T will become AF plus, this AF plus some A times ML MS. So this we already did. So with correction, it will become like this. So for our transitions, we are not considering this correction. I'm just saying that with the correction, it will be like this. Okay. With that a small probability of LS coupling. We are not considering LS coupling here because of the strong field or strong field Stark effect. We already discussed that the Stark effect or Stark splitting will be much higher than LS coupling or fine structure splitting. So we will ignore that LS coupling here, but still there is possibility of some small LS coupling. That's why we are having some error kind of thing with this star splitting delta. Okay, so with that error, if you consider, then you have to add this plus AML times MS. Okay, so Stark effect in hydrogen-like atom are all shifted by integral multiple of the fundamental amount from the original level. Okay, so if you consider the Stark splitting in hydrogen-like atom, then the splitting will be some shift. The shift of that splitting will be some integral multiples, or the shift will be some kind of a uniform fashion. Okay, so the Stark shift or Stark splitting will be kind of uniform fashion in case of hydrogen-like atoms. And the effect of the splitting effectors or splitting for first 3 levels, n equal to 1, 2, 3 for hydrogen atom. If you consider that scenario, we'll just here. We'll just calculate what is the value of n and n2, n1, and this is for the first 3 levels. Hydrogen atom. So that is n. That is I will just write here n equal to 1, 2, 3. So these are the first three levels of hydrogen atom we are considering. So for hydrogen atom, Z is equal to 1. We already discussed that. So for first three levels of hydrogen atom, n will be equal to n equal to 1. So what happens to the n equal to 1? What is we already discussed n1 will be equal to 0, 1, 2, 3, etc. up to n minus 1, and n2 equal to 0, 1, 2, 3, etc. So n1 will have values which is maximum of n minus 1. Since n equal to 1, maximum value that you can have for n2 as well as n1 is 0, because maximum you can have n minus 1. So n minus 1 is 1 minus 1, that is 0. And in second case, for the second level of hydrogen atom, that is n equal to 2, we'll be having n equal to 2. Then if n equal to 2, then you have n1 can have value 0 or 1, because n minus up to n minus 1 it can go. So n minus 1 will become 2 minus 1, which is 1. So it can take value 1 and 0 for both n1 and n2. So in the first case, let's take both are having value 1, n1 and n2 are having value 1. And then we take n2 is having value 1 and then n1 is having 0. Next case, n2 is 0, n1 is 1, or both are 0. All these values are possible, because when n equal to 2, n1 can take value 0 and 1, because n minus 1 is 1 here. So n2 also take 0 and 1, that is 0 and 1. So any of these combination can come 0, 0, 0, 1, 1, 0, or 1, 1. Any of these combination can come. And if your value of n equal to 3, then this n2 can take values up to 2. So that will give 2, let's say 2 and 2 first. Then I will take 2 and 1. Then I will take 2 and 0. I will complete one set of values for first one. So 1, 1, 1. And at the same time, it can take values 2, 1, 0. 0, 0, 0. For 0, 0, 0 case, it can take values of 2, 1, 0. So total 9 set of values are possible. Now what will happen to this n2 minus n1? We have to calculate the energy. So we need or this the wave number shift. So delta T we have to calculate. So n2 minus n1, what is that? In this case it is 0. Here it is 0. It is this is 1. Then we have minus 1. Then we have 0. Then in this case we have just draw a line here. That is over. And in this case, you have 0, then 2 minus 1 is 1, then 2 minus 0 is 2, 1 minus 2 is minus 1, 1 is 0, minus 0 is 1, minus 2, minus 1. Then you have n into n2 minus 1, n into n2 minus n1. That will be 0 here. Here it will become 0, 2 times 2, minus 2, 0. Then here it will come as 3 times 0 is 0, 3 times 1 is 3, 6, minus 3, 0, 3, minus 6, minus 3, and again. Okay. Now, what is the ml values? ml values, calculate that. ml, what is the expression? ml equal to, we already discussed this. So this ml can take values with respect to that n1 and n values. This is n minus n2 minus n1 minus 1. So if we calculate that values for ml, then first one is 0 because n is 1. So 1 minus 0 minus 0 minus 1. So that is 0. Second one is minus 1. How it will come? N is equal to 2. So it will come n equal to 2 minus second case n equal to 2 minus n2 is what is n2? 1. So 1 minus n1 is 1 here. It is also 1. Sorry, this one is not needed. So n is 2, n2 is 1, so minus 1. n1 is also 1, so minus 1. Then again minus 1. So this will give you minus 1. 2 minus 1 become 1, 1 minus 1, 0, minus 1. Okay, in the third case, what will happen? So it will come 2 minus, next is 1. So this is 1, it is 1, and then 1 is 0. So this is 0, and then minus 1. So this will become 0. So in the same fashion, so this will become 0. In same fashion, you calculate for all those values. So this will be again 0. Then it's 1, minus 1, 0, 0, 1. Then we have, we just calculate these values, minus 2, then minus 1, 0. Confirm these things. Confirm these are right. Minus 1, 0, and 1. Then 0, 1, 2. So these are the values correspond to those ml. Now at last we will draw the transition for this particular case. So the transition we have so if for n equal to 1, we do not have any kind of energy level because your values are 0 for that particular case. Your n is 1, but n2 minus n1 is 0. So energy will become 0 in that particular case. Shift in energy will become 0. So n equal to 1 state will not be having any kind of splitting because of that start effect. From n equal to 2 we will start. So for n equal to 2, and for n equal to 3 we will say. What are the values of n2 minus n1? So there n2 minus n1 we have to consider because that at n2 minus n1 will give you number of energy levels because your energy depends on that n2 minus n1. For delta T, if you consider, that is given by f some constant times. I will put it as proportion. So it is proportion to f times m times n2 minus n1, n2 minus n1. This is n2 minus n1, right? So your delta T depends on this. So if your n2 minus n1 is how many values are there? It depends on this, the energy levels. So n2 minus n1, if you consider for n equal to 2 case, we will be having values corresponding to this n2 minus n1 as 1, 0, and minus 1. You can get it from this table. From here, we have 1, 0, and minus 1 values for n2 minus n1. Similarly, you will be having values for n2 minus n1 for n equal to 3 as 0, 1, 2, sorry, 2, 1, 0, then minus 1, minus 2. So those 5 levels. So n equal to 3 will be having 2, 1, 0, minus 1, minus 2. Then what is that n into n2 minus n1? N into n2 minus n1 in each of these cases. So for the case of 2, we have n into n2 minus 1 is 6 because n equal to 3 here. So 3 into 2 will become c. N into 1. So this will become 3. This will become 0. Will become minus 3. This will become. And similarly here we have 1 into 2. 2 into 1. N into n2 minus 1. It will become 2, 0, and minus 2. Now we have to draw the energy levels for these states. So here, second energy level is so this energy level difference will be given by that E, you know that expression E minus E0 that you have to calculate how much is. And you take some position here, some original position somewhere here, and draw these energy levels accordingly. So this is a rough draw of that. And then we have 3 energy levels here. So this is not up to that standard, okay, because your n2 minus n1 values will be different and it depends on that energy levels. So just I'm just drawing these 3 energy levels. So separation of those energy levels I'm not considering here. This separation I'm not considering. I'm just drawing it roughly. Okay, so just showing that transitions. So these are the energy levels. Now, if you want to get these transitions, then we have to consider the selection rules. And the selection rules are for this Stark effect. Delta L will be equal to plus or minus 1. And delta J equal to plus or minus 1 or 0. And delta ML should be equal to 0 plus or minus 1. Delta MJ should be equal to 0 plus or minus 1. Okay, so if you consider that ML values here I will just put that ML values. So for 6, we have ML value which is 0. N into this value I'm saying from here. N into N2 minus N1 equal to 6, which is having ML value which is equal to 0. You can see from here in this table. So this is your N into N2 minus N1 value. So if you take that as 6, so this 6 is having ML value which is 0. That I am writing in the last. And if you take this N into N2 minus N1 as 3, okay, so what will be that ML value? Consider here, this is your N2 minus N1 into N, or N into N2 minus N1, and which is equal to 3 here. So it can have value minus 1, but there is another 3 here. So it can also have value which is 1, right? So these three can have values. There is one 3 here for n into n2 minus 1. It can have value minus 1. And another 3 here for n into n2 minus n1, which can have ml value is equal to 1. So for n equal to 3, sorry, n into n2 minus n3, n into n2 minus n1 equal to 3. In that case, we have ml value which is minus 1 and plus 1. Similarly, you fill all those values minus 2, 0, plus 2 possible for n into n2 minus n1 equal to 0 for n equal to 3 case levels, n equal to 3 levels. So these are for n equal to 3 levels, and these are for. And then we have again minus 1 for minus 3, 1 and plus 1 and 0. And here we have 0, minus 1, plus 1, and then 0. Now, if you take the transitions, so ml, delta ml should be 0 or plus or minus 1. Delta ml you have to consider here. For Stark effect, we have all these selection rules. In this particular transition, we have to consider this delta ml. And in that case, we have to consider selection rule as delta ml equal to plus or minus 1 or 0 in this particular case. So that delta ml, if you consider the transition from this n equal to 3 to n equal to 2 state, then delta ml should be equal to 0 or plus or minus 1. If delta ml equal to 0, delta ml equal to 0, which is, we already discussed this, delta ml which is equal to 0, which means that pi component, and delta ml equal to plus or minus 1, these are the sigma components that we already discussed in the case of Zeeman effect itself. So when delta ml equal to 0, it is pi component, delta ml equal to plus or minus 1, it is sigma component. So I will take first transition from here, from 0 to this n2 equal n2, that ml equal to 0. So I will just take this transition, talking about this transition. So what is the delta ml? Delta ml is 0 minus 0, 0 here, here also it is 0. So 0 minus 0 is 0. So that will give me a pi here. So this is a pi component. Okay. Next, I will draw next transition, which is from minus 1 plus 1 to 0. This one. This one to 0, the same 0, 0. So what is that difference delta ml? Delta ml is minus 1 plus 1 minus 0. So that will give you minus 1 or plus 1. So that is sigma component. So I will just put it below this line, baseline. So I will just draw it here. So this is my sigma component. Again, minus 2, 0, plus 2, 2, 0, minus 2, 0, comma, plus 2. So if you take that particular case, minus 2, and remember this particular transition, minus 2 to 0 is not possible, plus 2 to 0 is not possible, only 0 to 0 is possible, 1 0 is there, so only this 0 to this 0 is possible. Then only delta ml becomes 0. Otherwise, it will become plus or minus 2. Delta ml become plus or minus 2. Minus 2 and plus 2, if you take minus 2 minus 0 is minus 2, minus plus 2 minus 0 is 0. Sorry, plus 2 minus 0 is plus 2. So that is not allowed. Only delta ml equal to 0 or plus or minus 1 is allowed. So only this, from this 0 ml value, this transition is possible. So that will form my pi component because it is transition from 0 to 0, so that my delta ML is 0. So that will give me pi component. Again, I have the next transition which is coming from this line to this 0. So that will give me sigma component because it is coming from -1 and +1 ML value to 0. Then again, we have 0 to 0 transition, the last one. Again, giving me the pi component. So that is the first one for first state 0. Again, we have to look for the next state. So from 0 to this next one is starting from 0 to this second state of n equal to 2. Then again -1 to this -1 +1 to this 1 plus 1. So that will give me 0 in some cases. Again, from here to this one, from here to this one, transitions are possible. So from here to this one, 0 to -1 plus 1, what it will give? It will give either plus or -1. So that will give me a sigma transition or sigma component. The next one is from -1 plus 1 to -1 plus 1. So either it can give me -2 or +2, or it can give me 0, right? So it is a sigma component. -2 and +2 are not possible. So only that 0, that time equal to 0 is possible. That is pi component. Then -2, 0, +2 to -1 plus 1. So in this case, sigma component, only sigma is possible. If it is coming from 0 to -1 and +1, it will become -1 and +1, and -2 to +1, it will come -1. For -1 and -1, it will come -3. So that is not allowed. So those allowed case, if you consider, that will give me again a sigma component. And in the next case, -1 plus 1 to -1 plus 1, again a pi component, because it will give me 0, either 0 plus or -2. Plus or -2 is not possible, or it is not allowed. And the last one is 0 to -1 and +1. So that will give me a sigma component. So the whatever I am drawing below, which is sigma components, whatever I am drawing above this line, they are pi components. So these are pi components, and these are sigma components. Now the last one, which is the transition from all these n equal to 3 states, energy level splitting. So initially it is having only one energy level. Remember that this principal quantum number, which is having only one energy level, this n equal to 2 is having only one energy level. That n equal to 3 splits into 5 different energy levels because of the application of that external electric field, and that's why this star effect is coming. Okay. You just remember that this is what is happening. Initially, you have only n equal to 3 energy level states, and that split into 5 different energy levels because of the external electric field. And here also we have n equal to 2 energy level, which splits into 3 different energy levels because of the external electric field. So after that external electric field, only we have these different star components which are. Otherwise, it is just one single transition from n equal to 2 to n equal to 3 to n equal to 2, and that will give me only one particular single line. But when you are having that electric field, you will be having n number of different number of. In this case, it will be 15 number of lines. It will be spectral lines which is coming. So in this case, if there is no field, then it will give me only one single line. Okay, so the last transition is to 0 again from all these states. So that will come from here to final one. So this is starting from here. Okay, this is from here. Again, you have the transition from here. And the last one is this. Okay, so what will happen to this? Just check this. So here also we have 5 components. Among these 5 components, I will be having 5 components and 2 sigma components. So this is the strong field Stark effect or strong Stark effect, which will split in this case it will split this single line into 15 number of lines. So here 3 into 2 will come. 3 into 2 is 3 into 5, which is 15 lines. Total of 15 lines. So that 15 lines are this. You can see. So this in this case, this n equal to 3 split into 5 levels, n equal to 2 split into 3 levels, 3 into 5 will give you total of 15 number of lines. Okay. So this is the case without field. You can also write like this. This is the case without this, without field, means without electric field, and this is with electric. So with electric field, that n equal to 3 levels split into 5, n equal to 2 levels split into 3, and the transition of electron will happen from any of these states with the selection rule delta ml equal to plus or minus. I'll just put it here. Selection rule for this plus delta ml 0. So the delta L value also, all other selection rules also will come here. So in this particular transition we are considering, we are taking this selection rules. Delta L should be equal to plus or minus 1. Okay. Then we have all other delta J equal to plus or minus 1, 0. Delta Nj is equal to. So in this transition, we are taking this delta ml, which is equal to 0 plus or minus 1 for this n equal to 3 and n equal to 2 cases. Okay. Maybe you don't just consider L equal to plus or minus 1. Other also will come, all selection rules will come accordingly. If you consider that LS coupling, then we have to consider all the transitions. So this is the strong field first order Stark effect of H alpha line. What is that H alpha line? N equal to 3 to n equal to 2 line, that we call it as H alpha. So this H alpha line, if you apply that strong Stark field, that will become like this. So this H alpha line, this is the first order Stark effect, strong field Stark effect of H alpha line. Okay, 0. So this H alpha line, if there is no field, then this H alpha line split into. If there is no line, then there will be only single line, single H alpha line. If you have that external electric field, strong electric field, then we have 15 different spectra or lines which will be possible in that particular case. Okay, so this is the strong field Stark effect.